And hello and welcome. In this video we will be looking at some of the main points behind electric circuits. And by the end of the video I would hope you would know the following. You should be able to explain what is an electric current and how we can measure it. You should also be able to explain what a voltage is and how we can measure this. Very importantly, you should know the relationship between these two quantities, voltage and current. This relationship is commonly known as Ohm's law. You should be able to state Ohm's law, both in words and as a labeled formula. And finally, you should be able to define the concept of electrical resistance. So let's continue. Now, one of my most embarrassing moments in college was when I casually mentioned to a lecturer that an electric current was a flow of electrons. And he roundly berated me for what seemed like several hours. Now, while it was wrong of him to embarrass me like this, he did in fact have a point. Whereas a flow of electrons is an example of an electric current, it is not actually a definition of an electric current. So ever since then, I've used the following definition for electric current. I've said an electric current is a flow of charge or charge particles, usually electrons. Anything I highlight like this is a definition and is something you should learn. So if an electric current is a flow of charge or charge particles, let's talk a little bit more about these charge particles and how they fit into our model of the atom. Well, we're all familiar with electrons. Electrons are one of the three main subatomic particles. Subatomic means smaller than an atom. And these subatomic particles known as electrons have a negative charge, and we usually find them in energy levels outside the nucleus in atoms. Just to refresh our memory about atoms and our model of the atom, let's have a quick look at our model of the atom. This is what we think atoms look like. Well, experiments by Rutherford and his two assistants Geiger and Marsden in the years 1912 and 1913 showed that all atoms have a small, dense, positive center, which we now call the nucleus. The nucleus is composed of two particles, and we call these particles protons and neutrons. Protons have a certain charge. They have a certain type of electricity, which we now call positive charge. Neutrons, for their part, have no charge. They are neutral, they are uncharged, hence their name neutrons. In energy levels outside the nucleus, we have these subatomic particles called electrons. These have a negative charge. In normal atoms, there are the same amount of negative charge electrons as positive charge protons. So if we can get these electrons to move in a straight line, we have a flow of charged particles, and that is an electric current. That can be generally easy enough to do. It's easy enough to strip electrons off an atom because they are on the outside of the atom. Similarly, if we could get these protons moving in a straight line, we would have a flow of positive charge particles that would also constitute an electric current, but it's a lot more difficult to do. In fact, in the real world, when we encounter electric currents, it is almost always a flow of electrons we are going to be talking about. So, an electric current is a flow of charge. We've established that, and we've said how important it is. So, a flow of electrons will be considered an electric current. A flow of protons is also an electric current, but it's rare you would encounter that. But a flow of neutrons would not be considered an electric current because neutrons have no charge, they are uncharged, they are neutral. Clearly, electrons will not move themselves. They need some motivation, they need a force to move them. And this quantity that moves electrons, that moves charged particles, we call a voltage. So a voltage is something that will push a current through a circuit. I'm going to highlight that as a definition. It is not a perfect one, but it is a very good working one for the moment. Other names for voltage that have been used throughout the years, one is potential difference, or one I really like, a very old one, used many hundreds of years ago. A voltage can also be called an electromotive force. This is very meaningful if you think about it. It's the force that motivates electrons to move. So in other words, for a current to flow between 2 points, for charged particles, usually electrons, to move between 2 points, then you need this thing called a voltage between those 2 points. In short, you need a voltage to push a current. Now it's very important to realize how we can actually measure voltages. You may have encountered this piece of equipment before, but let's have a quick look at it. How is a voltage measured? Well, the instrument we use to measure a voltage is known as a voltmeter. There is the symbol for a voltmeter. It's just a circle, 2 wires coming out of it, and a V in the center. Here is an example of a voltmeter. In fact, this instrument really would be called a multimeter, but it can be used to measure both voltage, current, resistance, and some other quantities. But when we use it as a voltmeter to measure voltage, we call it a voltmeter. This mechanic is measuring the voltage of a car battery. You notice he connects one terminal of the battery, the negative terminal. He connects it to one probe from the voltmeter, the black one, and that goes back to the black connection on the voltmeter, and the other probe goes back via the red lead to that terminal on the voltmeter, and he has measured the voltage of the car battery as 12.78 volts. The units of voltage are volts. Similarly, we have an instrument that will measure current, and the instrument we use to measure current is known as a ammeter. There is the symbol for an ammeter, and here is an actual ammeter, or a diagram of one. Now it's important to know this is a particular type of ammeter. It's known as a milliammeter. So if it if the needle moved to 80 there, that would not be 80 amps of current. It would be 80 milliamps, or 80 thousandths of an amp. So the most this meter can read, the highest current it can read, the full scale deflection, would be 100 milliamps. That's 100 thousandths of an amp. That is 0.1 amps. In other words, a milliammeter is a more sensitive ammeter. And there is the diagram, or the circuit diagram, the circuit symbol for a milliammeter. You intend to encounter milliammeters as often as you do ammeters in this section. One thing that often causes a lot of confusion for students is how you place an ammeter into a circuit and where you place it. Well, here we have a very simple circuit with a battery, positive and negative, an ammeter in the circuit, a bulb, and back again to the battery. Here is the exact same circuit, only I've moved the ammeter to the other side of the bulb. And it is very important to realize that both of these ammeters will give exactly the same readings for the current flowing in the circuit. So if this ammeter reads 2.5 amps, the units of current are amps, then this ammeter will also read 2.5 amps. That tends to confuse some students who think that the current before a component like a bulb should be greater than the current after. But that is not correct. Current is not consumed or used by the circuit. The bulb will simply convert electrical energy into heat energy, so you might think of it that there's less energy, electrical energy going back to the battery, but the current will be the same everywhere in the circuit. So it makes no difference where in the circuit the ammeter is placed, as long as it is placed in series with the battery and the bulb. In series just means before or after any one of those components. In an earlier diagram, we saw the mechanic placing his voltmeter between the two ends of the battery, the two terminals of the battery, in order to measure its voltage. We say that a voltmeter is always connected in parallel or across a component in the circuit in order to measure the voltage between the ends of that component. For example, if we want to measure the voltage between the ends of this battery, we connect one end of the voltmeter to one end of the battery and the other end of the voltmeter to the other end of the battery. We say this voltmeter is placed in parallel with the battery, or between its ends, or across the battery. So a voltmeter is always connected in parallel with whichever component you wish to measure the voltage of. Similarly, down here we have a component known as a resistor. Now, a resistor can be anything that allows electric current to flow through it. It can be a piece of wire, it can be an electric motor, it can be a bulb, it can be any type of electrical component. And if we wish to measure the voltage between the ends of this resistor, we again place our voltmeter in parallel with it between the ends of it. So a voltmeter is always connected in parallel, whereas a ammeter, to measure the current, is always connected in series with a component. So here is an ammeter in series with the resistor and the battery. Current flows in these directions like this. There's another ammeter in series. So a voltmeter is connected across a component, an ammeter is connected in series with a component. And now we're coming to the main point of this video, to investigate the relationship between voltage and current. And to do this, I'm going to build this simple electric circuit. And I'm going to use electronic simulation software that's easily available free on the internet to do this. This circuit will have a battery. There's the battery, and there's the symbol for the battery. It will have some wire, copper wire like this. We draw copper wire just as a line like that. It will here have a resistor. There is a resistor. And it will have an ammeter in series with the resistor. Here is my ammeter in series. And in parallel with the resistor, there will be a voltage. The voltmeter. The voltmeter will measure the voltage between the ends of the resistor, and the ammeter will measure the current that's going to flow through the resistor. Now, the online software that will simulate an electric circuit I'm going to use comes from the University of Colorado. And they have a fantastic resource. You find it by just going to Google and typing in PHET, which stands for Physics in Education and Physics, Electronics and Technology, I think. When you Google that, usually the first website that comes up is University of Colorado. There it is. And you click into that website. You click on simulations, you click on physics, and you will find a whole range of simulations for electronic circuits and other things. But the one we're going to use is called Construction Kit DC. And I've already used this kit a little bit. Unfortunately, some of the components are just gone off screen for you there, but I have built this following circuit. The circuit consists of a resistor, and there is the resistor. In series with the resistor is an ammeter to measure the electric current flowing in the circuit, and in parallel with the resistor is our voltmeter. It's interesting to note that in the simulation you can see in the circuit, in the copper wires, in the resistor, even in the ammeter, you can see the electrons, and the electrons are not moving. Now, if we could get those electrons to move, that would be an electric current, because electrons are charge carriers, they're negative charge carriers, and if they move, we have an electric current. But the question I'm asking you is, why do you think these electrons are not moving? Well, we said earlier we need something to move those electrons, to motivate them to move, and we said that is a voltage. And a voltage can be applied by getting a battery. So here is my battery. So when I connect in the battery to the circuit, then you should see, and I make the circuit a little bit symmetric, you can see the electrons are moving now through the circuit. The battery has this quantity, this capacity called voltage. The voltage pushes electrons, and we have a voltage reading on the voltmeter and a current reading on the ammeter. So the next question we're going to try to investigate is, what is the mathematical relationship between voltage and current? In the simulation software, the battery is a property that real batteries in the real world do not. You can actually change the size of its voltage by clicking on it. In the real world, we have to use things called variable resistors to do this, but it's very, very handy to be able to do it in the simulation circuit. So what we're going to do is move the voltage to 0. And when the voltage is 0, as read on the voltmeter, the voltage between the ends of the resistor, then the current flowing through the resistor is also 0. That is not a surprise. We said a voltage pushes a current, so if there's no voltage to push a current, the current will be 0. Let's just increase the current in equal jumps and see what happens to the current. So I'm going to go up to a voltage of 1. Now there's 1 volt between the ends of the resistor, 1 volt across the resistor, and the current is now 0.1 amps. If I go up to 2 volts, the current has doubled up to 0.2 amps. You're going to see a pattern and trend here very obviously, very quickly. If I go to 3 volts, our current has gone to 0.3 amps. 4 volts, 0.4 amps. 5 volts, 0.5 amps. 6 volts, 0.6 amps. 7 volts, 0.7. 8 volts, 0.8 amps. So there seems to be a very, very clear mathematical pattern, a mathematical relationship between voltage and current. The larger you make the voltage, the larger you make the current, and there seems to be a mathematical relationship between them. So let's examine those results in a little bit more detail. Well, there's my circuit, and let's look at the results. Well, as the voltage got bigger, so did the current. That is not surprising. We said voltage pushes a current, so the bigger the voltage, the bigger the current. What is very, very interesting is if you look here, if you go from 1 volt to 2 volts, that's doubling the voltage, you double the current. If you go from 2 volts to 4 volts, that's also doubling the voltage. Similarly, the corresponding current also doubles. 3 to 6 is doubling the voltage. The current obligingly also doubles. And the last one I've got there is 4 volts up to 8 volts. The current also doubles. So the trend is, the pattern is, if you double the voltage, you double the current. What happens if you triple the voltage? Well, 1 to 3 is tripling, and 0.1 to 0.3 is tripling. 2 to 6 is tripling, 0.2 to 0.6 is tripling. So if you double the voltage, you double the current. If you triple the voltage, you triple the current. If you make the voltage 7 times bigger, the current becomes 7 times bigger. And that mathematical relationship, as you may well know, is known as directly proportional. So we come across this graph of voltage against current. I've just taken those readings, I put them on a graph, voltage on the y-axis, current on the x-axis. We'll explain exactly why later. And when I plotted them, I got a straight line through the origin. These are just the results we saw in the previous slide. And because I've got a straight line, of course, when you're plotting graphs, voltage in volts, very important to put both the quantity and the unit, current, the quantity, and the unit amps. If you get a graph that's a straight line through the origin, you can actually say, well, I know what the mathematical relationship between them is. Because the conclusion here is, as the graph is a straight line through the origin being the point where the axes meet, this shows that voltage is directly proportional to current. That is the mathematical relationship, that if you double one, you double the other. If you triple the voltage, you triple the current. That is known as a directly proportional relationship. In mathematical symbols, we write it like this: V for voltage, I for current, voltage directly proportional to current. Very important mathematical relationship. Now, let's just go backwards a little bit. Let's go backwards a little bit and examine these results again. Because I have a third column here, I have my voltage in volts, quantity in units. I have my current in amps, quantity current, units amps. But over here I've got my third column, voltage divided by current. You notice I left the first line blank because 0 divided by 0 in our type of mathematics is undefined. It's actually a big problem in mathematics, dividing by 0, but the other one should be okay. What happens if I divide 1 by 0.1, or 2 by 0.2, or 4 by 0.4? Well, I think most of you will have come to the conclusion that what you will get each time is 10. So in my circuit, no matter what the voltage was, no matter what the current was, if I divide voltage by current, I get this constant number here of 10. And we're going to find out shortly that this 10 has an actual meaning for the circuit. It has a meaning in physical reality. We're going to call this number the resistance of the resistor. Let's just examine the graph again a little bit. Well, there's our graph. But what I did next was I just got, as you have often done in mathematics, I got the slope of this graph. Now you get the slope. How do you get the slope of a graph? Well, you get 2 points on the graph. 1 point in this graph, because it does go through the origin, is 0, 0. And another point up there, I'm not sure which point I used. Then you use the famous formula y2 minus y1 over x2 minus x1 to get the slope of the graph. So let's just see what I did when I got the slope of this graph. Well, here's the exact same graph again, but this time I've marked 2 points on it, 0, 0, and 0.7, 7.0. I called 0, 0, x1 and y1. I called this x2 and y2. And I wrote down that I was calculating the slope. I wrote down the slope formula. You should be well familiar with that from mathematics. And I put my points in, and I got an answer of 10, 10.0. So the slope of this graph corresponds to my column on my column I had here, which is voltage divided by current. And as I said to you, we're going to talk about this as the resistance of the resistor, and more about that shortly. So what does all this mean? Well, as the graph is a straight line through the origin, we can say there's a mathematical relationship between two things, and that mathematical relationship shows us that the voltage is directly proportional to the current. As we said earlier, this means if you double the voltage, you'll double the current. Triple the voltage, triple the current. Multiply the voltage by 5, you'll also multiply the current by 5. So there's a mathematical relationship between them. And this mathematical relationship we know as, we call Ohm's law. It was first developed by George Simon Ohm, a Prussian, now modern day Germany, in I think the year 1824 or thereabouts. And Ohm's law states that the voltage in a circuit is directly proportional to the current flowing through that circuit. This is a very important relationship, so it's one that we should highlight. There's one caveat, there's one catch, and we'll talk about this later. The temperature of the conductor, the temperature of the resistor in my circuit must remain constant. And this is because the resistance of a wire, the resistance of a conductor changes if you change its temperature. So we're going to learn Ohm's law this way. Ohm's law states that the voltage is directly proportional to the current if the temperature of the conductor remains constant. It's also very important to know it in not only words, but in symbols. V proportional to I. They use I for current because C was actually taken for charge. So voltage is directly proportional to current, and if you use that version of Ohm's law, please label each part. Of course, if two things are directly proportional, you can always put a constant in to make them equal, and this constant is known as the resistance of the resistor. So we come with a relationship that a lot of you would have come across in junior cert: voltage equals resistance multiplied by current. Any of these words or labeled expressions will do as a definition of Ohm's law, and it's something you should learn very, very quickly. Now, we've said voltage is directly proportional to current, and we've said the constant of proportionality is this thing which we call resistance. In fact, in my humble opinion, in all of electricity and electronics, resistance is probably the most important concept, because all of modern electronics is about the resistance of different components changing under different sets of conditions. So resistance is something we're going to be focusing on very, very, very clearly from now on. So just let's do a little bit of mathematics. Well, first of all, what actually does resistance do in a circuit? Well, we're going to find out later when we look at real circuits that resistance is something that reduces or limits the current flowing in a circuit. We're going to find that if the resistance of a circuit is increased, the current is decreased. And if the resistance of a circuit is made less, the current will actually get higher. But from our point of view today, we can define resistance as the ratio of voltage divided by current. Why can we do that? Well, if voltage equals resistance multiplied by current, if I divide each side of this expression by current, then I get resistance equals voltage divided by current. And this is the definition of resistance. In a casual way, we'll often say resistance is something that reduces current in a circuit, but here is the actual definition. If you use this formula as a definition of resistance, and it's perfect to do so, in fact this is the way it is written in your mathematical tables, then please label each part. R is resistance, V is voltage, I is current. This is the formula that's used to define resistance, and we're going to find later that the resistance is measured in units called ohms. Voltage is measured in units called volts, current in amps, resistance in units called ohms. So a quick summary about everything we've actually hit upon today. Well, the first thing is a quick summary about everything we've hit upon today. First thing, an electric current is a flow of charge, usually electrons in the real world, but not exclusively, and the unit of current is the amp, which has a symbol of A. Very important, Ohm's law states that the voltage is directly proportional to the current if the temperature of the conductor remains constant. It is quite acceptable to put Ohm's law, write it like this: voltage directly proportional to current, as long as you label each of those. Or voltage equals resistance multiplied by current, as long as you label each term there. That would be very, very important. And it clearly follows on from this formula, voltage equals resistance by current, that resistance will equal voltage divided by current, and that's our definition of electrical resistance. Resistance equals voltage divided by current. The unit of resistance is the ohm. In the real world, resistance limits or reduces the current flowing in a circuit, but that isn't a definition, that's a definition there. And the resistance of a resistor is 1 ohm if a voltage of 1 volt causes a current of 1 amp to flow through it. In other words, when is resistance 1? Well, resistance is 1 ohm if the voltage is 1 volt and the current is 1 amp. That's a definition of the unit of resistance, the ohm. That is also something to learn. Okay, a couple of answers, suggested answers to that worksheet there. You can just go through this yourself. Notice that anytime I give an expression, I always label the parts of that expression. If anytime I give a formula, I will label that formula. And next time we meet, then I think the most important word will be resistance. Okay, resistance is not futile, it's voltage divided by current. Resistance in the next video. Okay, I hope this is some use to you. Take care and goodbye.